Welcome to an introduction to Dijkstra's algorithm, which is an algorithm that enables us to find the shortest distance from a starting source node to all other nodes on a weighted graph. So a weighted graph is a graph that is composed of nodes and edges, and each of these edges has an associated cost or distance. For example, moving from node A to node B requires a cost of 3 units. A constraint of Dijkstra's algorithm is that any of these edges on the weighted graph cannot have a negative cost associated with it. And the big O time complexity is big O of E log V, where V is the total number of vertices and E is the total number of connecting edges. Here is a step-by-step walkthrough of Dijkstra's algorithm on this weighted graph. So we start out by indicating the shortest distances from A, which is our arbitrary starting node. The distance from A to itself is 0, and the distance from A to any other node on the graph is indicated as infinity as a starting point. The reason it's infinity is because not all of the nodes on the weighted graph are necessarily reachable. And after we complete Dijkstra's algorithm, if any of the nodes' distance to A is still infinity, it means that that particular node is unreachable from the source node. We start by exploring the adjacent nodes from A. We have two options, B and D. We start by exploring A to B, which has a cost of 6. And since 6 is less than infinity, we replace that in our distance table. Next, we explore A to D, which has a cost of 1, and since 1 is less than infinity, we replace that in our distance table as well. Now we have to mark A as being visited since we've explored both of the adjacent nodes. It's important to realize that Dijkstra is a local optimization algorithm. So when deciding which node to visit next out of B and D, we have to always take the shortest cost or the minimum cost path. So next we explore the adjacent nodes to vertex D. Going from D to B requires a cost of 2, and going from A to D requires a cost of 1, for a total cost of 3 to go from A to B. Notice how our current total cost is 6, and 3 is less than 6, so we replace that in our distance table. Next, we explore the other adjacent vertex to D, which is E, and that has a cost of 1 to go from D to E, and there's also a cost of 1 to go from A to D. This gives us a total cost of 2. And notice how 2 is less than infinity, so we replace that in our distance table. Finally, we mark D as being visited since we've visited all the adjacent nodes. Now, following local optimization, we go from D to E rather than D to B. Now we're at E, so we explore the two paths associated with it. From E to B, there's a cost of 2, and going from A to E, that's a cost of 2 as well, for a total cost of 4. But notice how 4 is greater than 3. So there's no change in our shortest distance from A. Next, we explore E to C, which has a cost of 5. And the cost of going from A to E is 2, plus 5 gives us 7. And notice how 7 is less than infinity, so we replace that as the shortest distance from A. Next, we mark node E as being visited since we've explored all the adjacent vertices. Following local optimization, we move to node B and explore the unvisited adjacent vertex. It only has one, which is node C, and the cost from going from A to B in optimal terms is 3, and the cost of going from B to C is 5, which gives us a total cost of 8. But our current shortest distance or minimal cost is 7, and 8 is greater than 7, so there's no change in our shortest distance table. Now we mark node B as being visited since we've visited its only adjacent unvisited vertex C, and finally we move to vertex C, which has no adjacent unvisited vertices. That completes Dijkstra's algorithm on this weighted graph. Dijkstra is known as a greedy algorithm because it assumes that local optimization will lead to a globally optimal solution. The reason we optimize locally is because we're always visiting the unvisited vertex with the smallest known distance from the vertex. And the reason this has pitfalls is illustrated clearly in the diagram below. According to Dijkstra, which is a greedy algorithm, we'd be moving from A to B to C to D to E, while the globally optimal solution is clearly going from A to E. Here's Dijkstra's algorithm implemented in pseudocode. It's fairly easy to translate it into actual Java code, and I encourage you to do so.